Well, welcome. I'm John Elliott, the lab's Chief Sustainability Officer. This is one of our last formal presentations of a whole series of Earth Week events. And then after this, we will be having an electric vehicle showcase out in the cafeteria parking lot. And there will also be other resources there about alternative transportation. These events throughout the week have been brought to you by many across the lab that are interested in advancing sustainability. I refer to them collectively as Sustainable Berkeley Lab. I would like to thank one person in particular, Patrick Thorson in EHSS, who really made this week possible, put a lot of energy and a lot of spirit, and worked out a lot of details for the week here. We have today Venkat Srinivasan. He works with a team of researchers and is here at the lab and is program manager of batteries for advanced transportation technologies. Venkat's research is in understanding electrochemical systems in the area of storage devices, that is batteries and capacitors. The BAT program is involved specifically around looking at lithium-ion batteries and their uptake in the transportation system. So with that, I present to you Venkat. And immediately following this, out in the parking lot at noon, I encourage you to come out and see some neat electric vehicles. And then as well, if you Google Berkeley Lab Earth Week 2013, you can get the full schedule for the remaining part of the week. We do have a showing here in this auditorium today at 3 of Chasing Ice, a documentary documenting the effects of climate change on ice. So
thank you. I hope you cannot hear me because the battery light is on this thing, so hopefully that will not be a problem. So like it said, my name is Venkat Srinivasan. I think the batteries are bad on this one. And I'm a staff scientist here working on the batteries program. So the interesting part is going to happen at 12 o'clock. I'm actually looking forward to going and seeing all these electric cars. But I thought I'll throw up a question and ask this of everybody in this room. How many of you here have an electric car? Not. This is a bad crowd to be having this question. Isn't that what's going on? So maybe what I'll do is this, but I'll change the question to, is it in your future rather than is it in my future? That's because I have specific needs, I'm cheap, I don't like to buy things that are expensive, and so we sort of talk about where are we, how do we get electric cars to be something that everybody in the world buys. We'll talk a little bit about what those challenges are. So the way I've structured the talk is I'll give you a little bit of history, not a whole lot, a little bit. I'll do it in 2 different places in my presentation. Then I'll tell you a little bit about where we are in battery technology compared to where we need to be. And the need to be part is the one that is the most confusing. As we know, there are people sitting in this room who have electric cars. So the question really is, how do we get everybody to buy an electric car? Not just a few of you, but every one of you. How do you get there? And the Department of Energy has looked at this problem, and they have some numbers, and I'll kind of show that. And so I'll show you where we are compared to where we need to be. And then I'll tell you a little bit about what we, as in Berkeley Lab, the larger battery community, are sort of doing to bridge that gap. Okay, so that's going to be the presentation. For those of you who don't know, we have a fairly large batteries program at the lab. So some of it is in building 70 next door, some across the lab, and 62 used to be predominantly in EETD, but that has changed. Today we have people in MSD, in CRD, in the user facilities, in ALS, molecular foundry, all looking at batteries. So it's a growing community of scientists all thinking about the battery space. We're doing it not just for vehicles, we're also thinking about the grid. So think about a solar panel. I know that some of you have solar panels in your backyard, in your roof. Think about having a battery pack in your backyard to accompany that, right? So we're also thinking about that problem. I won't talk about that today. I'll just talk about electric vehicles, but I'll sort of touch upon the grid maybe briefly. Turns out batteries at the lab goes back many, many years, all the way to the 1950s. So it turned out during the 1950s, most people in batteries were working with water-based systems. So think lead-acid batteries, nickel-cadmium batteries. Everybody wanted to use lithium, but they could not because lithium reacts with water. And there was a professor at UC Berkeley, Charles Tobias, who's sort of the father of my field. He found a way to use lithium metal and plate lithium in certain solvent molecules. Those solvent molecules began all the research in lithium batteries. So in many ways, research on lithium batteries began at the lab. And what we've done in the last 50, 60 years since he started doing his work is we've made lithium-ion successful. All of you have one in your pocket at this moment. Your cell phone has a lithium-ion cell. My laptop has a lithium-ion battery in it. And ultimately, these batteries have actually moved from cell phones and laptops all the way to cars. And that's why today you see cars like this. The Nissan Leaf, which we were just talking about before I started the presentation. It's a great car. It actually is a fantastic car if you drive it. It's completely quiet. It's really beautiful to drive. And it drives like a normal car in many ways. It accelerates very well. It drives. And many of you might be having this car, so you probably love this car. But it turns out the Nissan Leaf has a problem. The problem is that this car has a range of somewhere between 70, 80, 90 miles, depending on how you drive. And a typical gasoline car, the car I own, has a range of 350 miles. My daily commute is approximately 70 miles. So for me, the Nissan Leaf becomes a problematic solution because it kind of cuts into the range problem and the range anxiety that everybody worries about. Charging these batteries takes a long time. Sometimes it's faster if you can find level 3 charging, but oftentimes it can be longer. So the question is, how do we bridge this gap so that we go from cars that give us limited range to ones that give us all the range that we need so that we don't have to worry about range anxiety? Okay. I have a neighbor who has a Nissan Leaf, so I was talking to him and I was asking him, how much did it cost you to buy it? And he said, oh, I didn't buy it, I leased it. And I said, why? He said, that's because battery technology is going to evolve so much in the next 2 years that it makes no sense for me to buy a car. Well, I don't want to point this out to him, but battery technology evolves at 5% a year. Okay, so that's the Moore's law for batteries. Okay, which means that if he waits a couple of years, all he's going to do is increase the 70-mile range to maybe 75, maybe 80 miles. It's not something that happens dramatically. Part of the reason for that, and this is one of the things that people get confused about, electrons and ions have to react at interfaces for batteries to work, and that tends to be a very problematic thing. It's not an easy thing to happen. That's the reason why we have a lot of difficulty getting huge improvements in battery technology. And I'll say a little bit about what we're trying to do to sort of change that. But that's the crux of the problem, right? We have a range anxiety problem. Batteries don't evolve very quickly. Well, turns out this problem has been solved. A company down the road from here, Tesla, has solved this problem. They have cars that can go more than 200 miles on a single charge, right? Fantastic. The problem is those batteries can be a little expensive, approximately $50,000 if you're going to buy a car that goes more than 200 miles. So what I'm showing you here is cost on the y-axis. It's dollars per kilowatt hour, so it's normalized to the energy for which you're going to pay the battery cost. And you can see what's happening to those battery costs as a function of time. You see a huge reduction in the cost of these batteries. These are small cells that you have in your cell phone and laptop. If you buy an electric car battery, what you have to do is you have to take those small cells. You've got to make them larger in some cases. You've got to put them into a battery pack. You've got to start cooling them. You've got to get a battery management system. All of this costs money. What I'm showing you up there is the cost when you do all of those things. When you take those numbers and you multiply by how much energy you need in your car to go 200 miles, it comes out to be in the order of $50,000. Okay, so that's the fundamental challenge that we face. What I'm also showing you are the targets the Department of Energy has come up with for everybody to drive an electric car. And they think you need to be down here at $125 a kilowatt hour. Today, we are somewhere around $500 a kilowatt hour. I'm also showing you the numbers for what people think we need to get grid storage enabled. Again, very small numbers in the hundreds of dollars a kilowatt hour. Maybe 3 times, maybe 5 times, a factor of 5, which we have to decrease these costs for us to bridge that gap. So that's the second big challenge, right? Its range is the first big challenge. If we try to solve that challenge, we have a cost problem. These batteries can be fairly expensive, making it very hard for an average consumer to afford them. So we compromise on cost by buying a lower range car. That's what everybody is doing today. What I show you in the bottom is the 2 ways people are thinking about approaching this. If you think about what I'm showing you there, it's dollars per kilowatt hour. I can decrease the numerator by coming up with low-cost materials and processes, or I can increase the denominator by finding higher energy materials that presumably hold the same cost. Okay. So those are the 2 approaches people are taking. But again, the problem in batteries is it's not just about energy and not just about cost. It's a multidimensional problem, so we need significant increase in energy density for the range problem. We got to decrease the cost, but we have to do all this without compromising on safety. All of us know that because of what happened with Boeing. We have to have great cycle life, maybe thousands of cycles. We've got to make these batteries last maybe 10, 15 years. That can be a problematic thing. None of your cell phones last 15 years. They all last maybe 2 years before the battery dies, right? And ultimately, we've got to have the power capability. They've got to work at low temperatures. They've got to work at high temperatures. It is a multidimensional problem, and getting all of these things to happen simultaneously tends to be the big deal when it comes to batteries. That's why the Moore's law for batteries is 5% a year and not 50% or 100% every year. Okay, so that's the fundamental challenge that we face. So what do we do about this, right? How do we make something better than what we have? And so what I'm going to do now is I'm going to show you a tutorial, right? How do we make a better battery? Well, it turns out all batteries have three things. You've got to have an anode, a cathode, and an electrolyte. You put them together, you have a battery. We've been doing this for a long time, for 100 years. We had lead oxide, we had lead sulfate, sulfuric acid, and we made a lead acid battery. We took nickel hydroxide, cadmium hydroxide, potassium hydroxide, we had a nickel cadmium battery. Lithium ion is the same thing. We have materials that serve as anodes for lithium ion, some that serve as cathodes, and some that serve as electrolytes. You put them together in various combinations, you have a lithium ion battery. If you change the materials, your battery's performance changes. What I mean by that is you can change the energy density, you can change the cost, you can change the power, you can change the safety by just changing the materials. This has been fantastic because what the community has been doing for the last 20 years is they've been trying to find new materials. So they've been playing the game of finding new anodes, cathodes, and electrolytes that can serve this platform, and we've been making batteries better and better. So the key to success in lithium batteries is trying to find new materials. Okay? And the success we've had till now has given us the Nissan Leaf, has given us the Tesla Roadster, and the Tesla Model S. So the question now is, if we continue to play this game of finding new materials, where can we go? So people have looked at this problem, actually, at the lab, and we've thought very hard about how do we change and make some of these materials successful in the future. And if you do the math on how much it's going to improve energy density of batteries, you get a graph that looks like this. The one on the left is today's lithium-ion batteries. The one on the right is what happens if you have these changes that happen one by one. New anodes, new electrolytes, and new cathodes. Ultimately, we're talking about doubling the energy density of today's batteries if you work with lithium-ion. Okay, so that's what many of us think is kind of a limit of lithium-ion, somewhere in the order of 2 times the energy density of today's batteries. The question then is, how do we go from 2 times the energy density to much larger numbers? How do I get to ones where the batteries are going to be going 350 miles on a single charge? How do I make them really cost-effective? If you want to do that, you have to think about a new paradigm, right? It can't be just lithium-ion. It looks like it has to be something outside of the lithium-ion space. This is where something that DOE started doing becomes very important for us. So DOE started looking at this concept called the energy storage hubs. So this is a concept of what Stephen Chu had when he started JBay, the idea of bringing together scientists and engineers of different disciplines all together under one roof to start thinking about the same problem. And if they do that, presumably innovation can happen, new things can come out of it. He started an innovation hub like that in the area of batteries. So what happened when that happened was that Argonne National Lab led a project to compete for this. Berkeley is one of the partners in the hub along with other institutions. I show you the institutions. The goal of this project is what I call the Moonshot for batteries. What the project aims to do is it wants to make a battery that has 5 times the energy density at 1/5 the cost in 5 years. Now think about that for a few minutes, right? I just told you that we evolve at 5% a year, which means we double every 15 years. So this particular project is aiming to completely change that by doing something pretty dramatic. Now, people look at that and they say that's impossible. Well, that's the whole point of a hub, is to do something that looks impossible and try to come up with ideas that can get you there. So the kinds of things we're doing here are pretty significantly different from the kinds of things that have been done in the past. The idea being that if you can do things that are completely different, maybe you will find something that is so different from what we've been using till now that you can change this range paradigm and the cost paradigm that we're stuck with today. Okay. So that's the purpose behind this hub. It's a new thing that we're doing in the United States. It's going to reinvigorate research. We're going to start finding new things. Berkeley has a fairly large role in this enterprise, and I'll spend a couple of minutes just talking about that. The first thing we're doing is we have this project called the Materials Project that Christine Pearson in EETD started along with the people in our computational division. The idea here is that if you want to find new materials for batteries, the way we've done it in the past is you actually go into the lab, you make a material, and then you go make a battery with it. You test it and see what happens. I call it the cook and look approach. You go cook something up, you go look and see what happens with it. Right? Today, we can do this on a computer. We can actually calculate the voltage of a battery, and we can calculate the capacity of the battery, all sitting in front of a computer. And you can actually start narrowing down the kinds of materials you have to go make in the lab. This is an amazingly fast way in which you can narrow down the kinds of things that could be useful for you. They're going to be doing that as part of this hub and making sure that we find completely new things, hopefully, things that we don't have seen in the past, things that can make a big difference in the future. The second thing we're going to do is we're going to make those materials. And I'm showing you a couple of examples of things we're going to make. One of them is a membrane material. The second is a hierarchical cathode or an anode structure. The idea here is that we want to take advantage of the material sciences division and the molecular foundry and the expertise they have there to try to find a way to take those materials that are coming out on the left side and put them into these structures that we can then build into devices. The devices we'll also be building at the lab, these are going to be hopefully unique devices, things that are going to be much more efficient than the devices that we've built in the past. Again, building on the strengths of the lab and trying to make batteries from materials. We'll be building on those strengths to make something much better than what we've done in the past. Oftentimes when you make materials and you make devices, they don't work very well. That's the history of batteries. So what we're starting to do is starting to think about how do we understand what's going on by using our ALS facility, the in situ synchrotron facility that we have there, starting to understand what happens at the level of the electrode-electrode interface. What happens at the interface? How do we make things better? Okay. So the idea here is that we have a strong team at the lab, outside the lab, all working together, trying to find new materials. Our hope is that in 5 years, we'll find something much better than what we have today. But remember what I'm telling you. They're going to find new materials, things that are maybe small number of grams, maybe small cells, maybe slightly larger, nothing huge. If you think about what your car battery has, it has a fairly large footprint. It's actually probably this tall, it's probably this wide. So how do you go from a small amount of material and how do you make something that large? So how do you manufacture? That's the question. Turns out this is a big problem in batteries. So if you look at the history of battery research and manufacturing across the globe, and if you sort of look at what has happened in the past, there's a lot of research that happened in the past in the United States, a lot of it in California, on batteries. There was some stuff going on in Europe, certainly some stuff going on in Japan. This was a picture some years ago. If you look at manufacturing, maybe 20 years ago, much of it started happening in Japan. And that's because of a variety of things that we won't get into, but obviously I can talk to any of you about that. It's a fascinating history of why it happened, but most of the manufacturing started going on in Japan. Time went on, and as everything else, Korea started coming into play. They started manufacturing. Ultimately, most manufacturing today happens in China. Okay. A lot of research in the US, all the manufacturing happens in China. Guess what? Slowly but steadily, there's a lot of research now happening in those countries. Makes a lot of sense. They're making the batteries. Why don't we try to find a way to make them better? Let's work on new materials. Makes a lot of sense. So the question now is, what are we going to do when we find the new materials as part of the hub? Are we going to take those materials and ship them off? Are we going to do something with them in the United States, right? So we've been thinking very hard about how to reverse this manufacturing trend that we've seen in the past, where everything kind of goes away and we outsource everything, and how do we sort of bring them back to the United States? That is something the lab is working on very, very hard, and I'll sort of spend a couple of minutes just telling you what we're doing before I take questions. Let me remind you of the challenge that we're facing. Left side is where we are today, low-mile electric cars that are kind of expensive. The right side is where we want to be, a lot of range with very little cost. To do this, we have to do multiple things. We have to find new materials. That's the left side, and that's what we're talking about in programs like the Hub. But it's not just about finding materials. We have to find a way to make them manufacturable, and we have to manufacture them, and that's what is not happening in the United States today. And ultimately, we have to think about the market, right? Are you selling the battery to vehicles? Are you selling it to the grid? Are you going to be doing some sort of a fancy stuff with your battery by plugging the battery into the grid and trying to use the battery for different things? All of that matters. So it turns out it's not just about any one of these things. You have to think about all of these things to be successful, and if you want to make innovations in batteries happen faster. So I would argue that the best way to do this is by co-locating everything. If you have the research, the manufacturing, and the markets all in the same place together, history has shown us that you can have amazing things happen. This happened in Silicon Valley many years ago. It happened in the pharma industry in Boston, in San Diego, and in San Francisco. Something like this is needed if you want to have innovation happen much faster and if you want to make a big difference. It's, again, not just about doing research in isolation. It's about bringing together research with manufacturing and thinking about the markets that you're going to sell into. This ecosystem exists in a couple of places. It exists in China. Right? They have the research, they have the manufacturing. They're certainly going to be using all those electric cars, so they have the markets. But it turns out it also exists in California. So if you look at the California ecosystem today, we have a number of different companies. We think it's more than 40, all focused on energy storage. These are companies that are making anode and cathode materials, companies that are assembling them into devices, companies that are making battery packs, battery management systems, equipment for making these devices. We also have car companies, Tesla is one of them, We have Mission Motors. We have Zero Motorcycles. We have companies like PG&E that are interested in batteries for the grid. And we have all the consumer electronic battery users in California, right? We have Qualcomm, we have Apple, we have Intel. Everybody is looking for better batteries. And we've got some of the best university and national lab systems in the United States, all right here in California. So what we're doing in the lab is we're pulling all of these things together. We've formed a consortium called CalCharge. Cal is for California, and Charge is for charging a battery. So you can imagine a bunch of scientists sitting in a room and thinking about names. That's what we come up with when we do that. So the idea behind this is that Berkeley Lab has teamed up with CalCEF, which is the California Clean Energy Fund, and SLAC, the linear accelerator in Stanford, to start this regional accelerator. The idea is that you will find a way to connect companies to the universities and the labs so that we can take the research that we're doing as part of the hub, as part of the other programs that we have, move them to industry, work with industry in making them commercially successful, think about the markets they're going to be selling into, and try to put the whole pieces together. I will stop with this in the interest of time and take questions so that we can sort of have a conversation on this. Yes, sir. I think there's a mic. And
we have a live streaming audience. So.
Okay. I didn't notice much discussion about speed and accessibility of charging in all of this discussion, right? And I think speed of charging, for instance, could be something that could contribute quite a lot to the people using this. If you could charge as you're stopped at a store or whatever.
Correct.
Right now, it just is not practical whatsoever to do that.
That's right. So you will have noticed that Tesla has come up with these superchargers, the idea being that you will have a way in which you could do this very quickly. So there are different ways to think about this problem, right? One of them is to say, hey, let me just find an electric car battery that gives you all the range you need. You don't care about charging it quickly. Another way to do this is to say, let's have a huge charging station infrastructure. Let's try to find ways to do fast charging. And then let's try to see if we can get this market to go. Fast charging is a problematic thing in batteries. It's not easy to do it. You can probably fast charge maybe 30 minutes and still maintain the life. But if you're thinking about a 5-minute fast charge to a large difference in capacity, meaning if you want to get 80% of your capacity in 3 minutes or 5 minutes, it will have detrimental effects. In some chemistries, it's more than others. That's been the challenge, is thinking about, can we do fast charging? The second challenge has been the grid people are reluctant when they hear that there are going to be a bunch of batteries that are going to be plugging in for the amount of electricity that they're going to be looking for. So there is a grid challenge, but there's also a battery challenge. Those are the two big things why fast charging hasn't picked up yet. But we'll see what happens with Tesla. That should be an interesting experiment. So. Yes, ma'am. You probably have to wait. Or I guess I can repeat the question.
Can you speak a little bit about battery waste and where that's going in the future? Thank you.
So you might know this, but I'm going to get this number wrong. The problem with being recorded is somebody can verify that I'm doing this wrong. 80% of a lead-acid battery is recycled, give or take, something like that. So when you have a car battery, typically you're not just throwing it away. Somebody's recycling it. The lead comes back to the battery industry, actually. So which is amazing. We don't quite do that with lithium-ion today. But people are starting to think more and more about that. And I think as more and more vehicles start getting bought with lithium batteries in them, then I think there will be a demand for recycling, and there will be value for recycling. And I think you will see that happen. It's slowly beginning, but it really is not anywhere close to what we have with the lead-acid battery industry. So. But it's a problem that people are thinking about. So. Other questions?
Can you talk about standards and what the models are? I guess I'm thinking that in any nascent industry there are usually tries and attempts and different proprietary methods that could leave early adopters left out in the cold once a
there's a great story for that. So there are some standardizations. So the plug is standardized, so the charging plug is standardized. The greatest story for how standardization has been a problem is Better Place. I don't know if you know Better Place. It's a company, the business plan is kind of straightforward. It's the idea of saying, let me think about the battery like gasoline. So I'll pull up at a battery station, they'll pull out my old battery and push in a new battery. And then I'm off, I'm running. The recharge is 5 minutes. It's an amazing idea in some sense. The problem with that, there are a few different problems with the concept. One of the problems with the concept is people put batteries in all sorts of places in their car. That Chevy Volt has it in the middle, which you're not going to remove that one. The Tesla has it in the bottom now. Some people have it in the trunk. People are doing very unique things with where they're putting the battery. The second thing they're having is every car company has a different battery they're using. And so it's not as if everything is standardized. So the way you charge them is going to be slightly different. The voltage you might get to may be slightly different. That's not standardized. And that's because that's where we are in the industry. We have a number of different materials that are solutions. And different companies are saying, that's my unique selling point, is I have a material set that looks much better than somebody else's material set. And because of that, it's very difficult to develop a standard for that. So what I think we will see in the industry is more of a maturation of time. Things will go away. Some things will become better. They'll evolve. But it's going to take some time for that to happen. I think there are certain places where standardization will help. But where we are with battery technology, it's not obvious to me that we'll be doing anything completely standard at any point in the next few years at least, especially in terms of how the cars are designed, I think, to put a battery around it.
But you said the plug standard is the plugs are standardized now?
Correct.
Yeah.
Other questions? Thank you. I guess we'll all walk to the other side of the cafeteria to see the electric cars.